boundary conditions and so on. So these are all fairly standard things. And in this particular case, actually in our simulations, we use lamps, which is a very well-known MD package that is available open source, and it has a visualizer, and these are some of the parameters we have used. We use the Errico potential in modeling silicon substrates. We use actually Tersov. And then for the interaction at the interfaces, we use Lennard-Jones for the simulation of the interfacial interactions. One issue with when you try to do these things, and again trying to relate it to sort of like what we can normally measure in laboratories. Anyone who is familiar with mechanical testing knows that the experimental strain rates are these. Okay, and so experimental strain rates are fairly sort of like high strain rates, but we cannot actually do this in MD simulation. It's extremely expensive, right? And it would be sort of like impossible. So all the MD simulations are done with very high strain rates, and high strain rates that on the other hand no machine can, a physical machine can ever simulate. So we of course we have to go with that, but we also look at to the extent possible how does the strain rate actually affect our simulation. So one thing we started was actually to take a sort of like basic graphene sheet and assume that there are some defects and try to understand what happens to the strength of the graphene sheet at various temperatures. So here is a simulation. So what I show you here is a basic graphene sheet, and where randomly we have created 2% vacancies. Okay, so 2% vacancies, and what we do is actually, because it is random, we create 5 systems like that. Okay, so not just one random system, 5 systems, we simulate that. And these are the simulations at various strains. Okay, and you can see that sort of like the bonds are breaking, and then you can actually take these results, you calculate the potential of this system, and then on the basis of that you can get the stress strain curve, and on the basis of that one can find actually the strength of the sheet. So one can do this simulation for various amount of vacancies, and then different strains and so on, and that would actually give you sort of like fairly nice representation of what is the strength of graphene at different temperatures and so on. So if you want to do this, of course, fine. If you have a MD package, you can go and do this many times. It's good. But we try to do sort of see whether we can find another shortcut to get this result. And here we actually use one of the well-established principles, which is related to what is called the Bayes' principle, which says that the fracture initiates when this condition is satisfied. Okay, and this tau here is called a durability function, and that is the temperature, and then that is the time, and TF is the time to failure. And then what we do is actually we get the durability function using the Arrhenius formula. This is a very well-known thing when people study feed rates and so on in materials. We use this kind of formulation. Okay, so there's a constant here, activation energy, and the Boltzmann constant, and the temperature in Kelvin. So take that one, and we take this equation and we further expand this into this form, where tau 0 is actually the vibration period of carbon atom, which is about I think 2 nanoseconds, and n is the number of bonds, U0 is the bond energy, vacancy concentration, K is a constant, and this is something that depends on the chirality. And this is an equation that we have developed using MD simulations. So we try to get a stress-strain relationship, okay, and using MD simulation. So there is some kind of, like empirical sort of, curve fitting that has to be input into this. And then we try to solve this equation, okay. So solving this equation is pretty straightforward. You take some time and then you integrate this one, you plot that one, you plot the right-hand side, and then where the two things means actually is the fracture point. So you can get fracture point for different temperatures, okay, and then we have this relationship. And so now we can actually go back and then we can try to simulate, okay. We can try to simulate what we can get from that simple Bayes' principle and Arrhenius model, right? And what we would get from the MD. So you can see I'm comparing what the sort of the continuum type models gives me, and then also the MD gives me, right? So you can see that actually, for all practical purposes, what you see between the two systems of results actually are pretty good, okay? And the good thing is that certainly, in terms of the amount of computation needed, this one is about 10 to the power times 6 faster than the MD simulation. And the same thing is now being done, of course, the same type of same expression now being looked at the strain rate dependence of the strength. So you have the MD, you have what is given by the model. Again, MD for two types of graphene sheet. One is zigzag, the other one is armchair. And again, you can see that, here's of course it's not perfect agreement, but for all practical purposes, within about 10%, you can get pretty reasonable results. Strain rate calculations, similar. So strength and temperature against strain rates. So as I said that, these are the MD simulations that we have done, right? But these strain rates you can never even simulate by MD because it would take a huge amount of time for us to do at those strain rates, right? But the model, the sort of the continuum type model allows us actually at least look at what would be the rates, and assuming that it is working well in this range, we might be able to say that at least this is gives us a reasonable understanding of how things behave. The next one is now try to sort of, now these are sort of randomly dispersed defects, right? But if you have, say, for example, a row of atoms taken out, then what you would have a graphene sheet, which would have something very similar to a crack in sort of, a very well established problem in fracture mechanics, right? So here is the system. So, this is, you can consider this is a graphene sheet, and you have a row of atoms missing, right? And how can you sort of, simulate something like this? And actually what we did was we analyzed this problem using MD. So we did a lot of MD calculations for a system like that, okay? And we actually calculate the sort of the stress acting on this tip region using MD calculations. And so if you take sort of, the atoms in that region, you can calculate what is the equivalent stress in that region, right? And then you can actually plot curves, and that shows behavior which is very similar to what you would find in the classical fracture mechanics. The square root singularity, everything actually is simulated, right? And so here, so knowing that, we have a paper in International Journal of Fracture actually on this that was, I think, published about 2 or 3 years ago. And so we have this system, and what we are doing is we have the Griffith's energy balance, right? Which is given by this equation. It's a very well established equation. And then there is a paper actually that describe the model when you have discrete systems. Then one can replace this by a model like that, and where you can see that the strength of the pristine sheet, the crack tip radius is defined as basically this dimension, and fracture quantum and so on. All these things can be calculated actually, and so we took this one and we actually apply. So this is basically a continuum kind of idea, right? So you can take the Griffith idea for a graphene sheet. You can calculate gamma S. You can find actually Young's modulus that is strain dependent, okay? And you can basically, for different crack lengths, you can apply what would be the sigma ultimate. And you can see that, so MD is here. So MD at 1 Kelvin is that. And MD at 300 Kelvin is these results, okay? So you can clearly see that actually Griffith is kind of, like, it's not bad, it gives you the sort of, a similar trend, but the values are certainly not very close, right? But again, they are not sort of, like twice off or 3 times off. But then if you look at all these values, they are still within sort of, like 30–40% off. But on the other hand, this quantized fracture mechanics formula, that is this one, when applied into a system with these properties determined appropriately, actually gives you results that are pretty reasonable. Okay, so again you can see that what you can get here is some of the concept that you see in continuum, even though like this is nanoscale type structure, right? Some of those basic ideas in fact can be applied with some sort of condition that they are not the exact solution, but they give you a fairly a reasonable result. So now we actually took the same thing and we tried to take the previous model and we tried to modify that to include temperature. We try to modify that into actually take into defects and so on. And so here you can see that the model with MD with pristine, this is the continuum model that gives us result. This is MD with the defect, right? And so this is the crack length, and again at different temperatures, you can see that the ultimate strength actually reduced with temperature. But the interesting thing is that the model, which is requires far less computations, it gives us a fairly good approximation. Now, another problem that we have been looking at is that what happens when you bring other types of atoms into this system. So as I said that one of the common atoms are hydrogen. So if you have hydrogen connected into graphene sheets, okay, how do we do that? Now that actually changes some of the hybridization, because some of the bonds actually change the form from sp2 to sp3, and that using lamps we can actually model this. So here is a simulation that was done using lamps. At 300K, this is a pristine graphene sheet being pulled. So it's a simple stress strain curve, and then we add 1% of hydrogen atoms, okay, and 10%, 30%. So you can see that basically what it does is it reduces the fracture strength substantially, okay. The fracture strength is reduced substantially. It fails earlier at a lower strain, but the initial stiffnesses are sort of very similar. And so this is the same thing at 10% concentration of hydrogen additions, and then at different temperatures. So you can see that as the temperature increases, the graphene sheet actually softens and fails earlier. but the stiffness has very little influence on the temperature. Now we take this one and we try to actually see whether we can use that simple formula involving the Bayes principle and Arrhenius formula, and we modified the function to include chirality as well as atom concentration by adding sort of like a constant, and we related that chirality one can be actually related into the this diagram, which gives you the zigzag and the armchair directions with the angle of pi/6, and this is any arbitrary chirality, right? And you can show that this gamma there is equal to approximated by cos theta. So we had that equation, and then actually we had to solve this one. And I ran into a prof in our mathematics department who actually solved this for us exactly. So, so the solution for this was, she found that there is a solution for this one, which is given by this error function. Okay, it involves the inverse of the error function as well as the error function. So it's very, very interesting because now you have basically a closed form solution. Okay, and so you can basically simulate that, and once again it works very well, right? So this is the pristine sheet. This is 1%, and these are the MD simulations, right? So so the results actually are pretty good as far as the agreement between the things are, but obviously they are not going to be sort of perfect agreement. Here we are showing strength and temperature for zigzag. Previous one is armchair. This is armchair. And strength, this is with strain rates. And so you can see that pretty reasonable comparisons. And this is sort of a plot of how strength will vary with hydrogen percentage and temperature. So you can see that the strength will substantially reduce as the temperature increases as well as the hydrogen concentration increases. Same thing with respect to hydrogen and chiral angle. Okay, and